How would you like to 3D print much faster than usual and retain amazing print quality? Well, today I'm going to show you how using an accelerometer with Klipper's amazing input shaping on the rat rig. This is a video that I'm really excited about. It's one I had planned from before the build started and pretty much the reason I chose to make this printer. The input shaping that you'll see in this video I think is a significant step forward for 3D printing, particularly when set up automatically with an accelerometer. Last episode in the build series, we wired everything up, installed Klipper, did some basic checks and a first print. This episode is all about pushing the potential of the printer, but before we do that, let's answer some questions. This one's come up a lot. Can the kinematic bed be used for non-planar printing? The way I see it, the firmware already has independent control of each Z axis. This can be seen in this awesome demo video, as well as when we do the Z tilt leveling, as demonstrated in the last video. So to me, it's like adding a new mode of movement to a CNC router, such as this fourth axis. Toolpath calculations are going to be completely different to regular 2.5D milling. So for me, the potential is there, but it's the slicer that's actually going to hold things up and need a lot of development to make this happen. There was also some people interested in seeing the enclosure on this machine for high temp filaments. Because I have an enclosed Ender 5 already, you might be disappointed to hear that I'm not intending to build an enclosure for the rat rig. So my suggestion is to head to their Facebook group where some users are doing some really awesome enclosures and you can find out how effective they are. Since the last video, I've also been customizing bits and pieces of the printer, so let's quickly cover that. My previous video to this one showed some customization I'd done to the machine. In the last episode, I had the mains input power plug simply floating in space. So I designed this panel for the front that slots into the rat rig frame, and this rear housing with a 5V USB car adapter to power the Pi. It also powers an old Android tablet, which I'm using as a display at the front of the machine. In addition to this, I used the CAD model available for the printer to come up with this template for insulation under the bed, which I laser cut out of 3D printer packaging left over. The sizing and fitment was perfect, but I'm going to need some high temp tape to stop it from sagging down and to get a nicer fit. Another part I replaced was the generic filament guide, remixing the original step file to take some PTFE tube, which acts as a reverse Bowden setup, which is basically just a convenient and neat way to guide the filament from the spool to the top of the extruder drive. I also designed this bracket to take a webcam using a tripod bolt, and this can be mounted on either front corner of the machine. Plug it into the Pi and then reboot, and the webcam shows up with no additional configuration. I also added some bright 24V LEDs on the front of the webcam, and I connected this to the previously unused third hot end output. I then added this as a custom pin called LED pin, added macros for turning it on and off. This adds some buttons to the interface to quickly and easily turn the LED on or off. And I also use Klipper's delayed G-code command to turn it on automatically after the printer boots. The STLs and source files for all of these are available on Thingiverse, and I did fix the missing electronics panel DXF. One question that came up is whether Fluid and Mainsail supported as many plugins as Octoprint. I'm still a noob with this, so I defer to Mikkel, one of the rat rig developers, who gave a comprehensive answer. My patrons did point me towards this excellent tutorial by Vez3D, and I was able to follow it to a T and produce my first time lapses on the rat rig. Time to proceed to some basic calibration and tuning. I started by calibrating my E-steps, which is called something different in Klipper, but can still be calibrated the same way, by manually extruding a set amount of filament and measuring to see if this was accurate. Like last time, we don't want to edit the linked configuration files, so we copy and paste what we need to change into our main configuration file, then save and restart. Following this, I printed a single wall cube, which I then measured with calipers to see if the measured wall thickness matched the target from the slicer. After adjusting this, I printed the same cube, squished down and solid, just to make sure I didn't have any gaps or bulges in my extrusion. On my calibration website, you can tick the additional start G-code and add specific commands for your printer, including priming. I then generated a retraction tower using the inbuilt form, which is completely Klipper compatible. The results were pretty consistent, so I didn't change much for now. All of these sequences and how to use my calibration website has been covered in a previous video, which I've linked down below in the description. With the basics out of the way, I could now turn my attention to some Klipper specifics, starting with pressure advance. I've made videos on Marlin's equivalent linear advance before, so if you want to learn about the theory, please click the link in the description. Here's how the tuning process works for Klipper. We're going to be following the tuning pressure advance page supplied by Klipper, and that will take us through how to print this calibration tower. So the first thing we need to do is download the linked STL. We slice it as per the instructions with a 0.3mm layer height, 0% infill, and our default printing speed of 100mm per second. We preview the G-code and then upload it ready to Klipper. Before we print, we need to copy and paste some commands from the instruction page. This is really simple, just paste into the terminal and click send. We then return to the instruction page where there's a second command to copy. We paste this into the terminal, hit send, and that means we're ready to go to the Jobs tab and start the print. What's happening here is similar to the calibration towers generated by my website. The pressure advance value is constantly changing throughout the print, and we can verify this on the log. We can see it's constantly creeping up, controlled by the firmware. I actually followed the instructions and stopped the print prematurely because it was clear to me the best region had already come and gone. When we calibrate linear advance for Marlin, we're examining a series of extrusions to find the smoothest one. Here we're looking vertically up the tower to find the best region. My choice of filament makes this hard for you to see, but there's a marked difference in the corner quality, with the corners at the bottom of the print being quite bulgy, a crisp edge in the middle, and then as we head towards the top, they start to round. We have a similar situation with the internal features, where they're bulgy down the bottom, crisp in the middle, and starting to round and disappear up the top. Our job is to measure from the bottom the point at which we think the model looks the best. For me, just under 13mm. We then follow the formula on the web page, which if you follow the instructions simply means putting in our distance and multiplying that by 0.005 to find our ideal pressure advance value, which we then insert into our printer configuration file, and we can see here the standard value was very close to what I tested, which explains why my initial uncalibrated test cube looked pretty crisp. Save and restart and we're done. Just like Marlin, Klipper's pressure advance is best tuned for each individual type of filament that you use if you're after the best possible results. But now onto the main event, input shaping, and we're going to start with explaining exactly what it is. Let's start with the problem that it's trying to fix. As we increase the speeds and acceleration on our machines, they start to vibrate from the load, and that introduces an artifact known as ringing or ghosting. This is probably the #1 deterrent to cranking up the speed and acceleration on most 3D printers, and input shaping can magically reduce it. The thing we need to understand about the ringing is that it's not random. In fact, if you look at this image, you'll see that all of the ghosted patterns are the same distance apart, and that's because of the printer's resonant frequency. Many systems have a resonant frequency. It's where vibrations will naturally be the strongest. Musical instruments use this to effect, using set resonant frequencies to play specific notes. Another example is if you push a child on a swing, or as I prefer, karate chopping a gymnastics ring. You can see that my inputs need to be timed just right to accelerate the system, and that's the resonant frequency of the pendulum. If I disregard this and offer random inputs, we can see I'm no longer in tune and the system is all over the place. So back to our 3D printer. If we know the distance between the oscillations and the speed that we were printing at, we can determine the resonant frequency, and that means if we're using a firmware with very precise control of stepper motor timing, we can shape the input to the stepper motors and cancel it out, just like this chicken is able to cancel out most of my motion and keep its head in the same position. At the time of recording, Klipper is the only firmware that offers input shaping, hence why I chose it. RepRap firmware has experimental accelerometer support, and input shaping is scheduled for a future release, but as you're about to see, Klipper has it working extremely well already, so let's set it up. For this one, we're going to be working from the resonance compensation page, and the first thing we need to do is download the ringing tower STL and slice it with the suggested settings. Here's mine sliced. As we can see, I've done it with a single perimeter in vase mode, and I've locked the speed at 100mm per second for inner and outer layers to make sure the speed is definitely that. As per the instructions, we're going to edit our main configuration file to limit the acceleration, the square corner velocity, and also an empty heading for input shaper. Following this, we restart the firmware to load the changes. With our sliced file uploaded and ready to go, we refer back to the instruction page and once again copy and paste some settings. The first temporarily shuts off pressure advance, the second one turns off input shaping, a bit redundant at this stage, and the third one is a tuning tower command similar to the one we used when tuning pressure advance. With these three commands input, we can now switch to the job tab and start our test print. This print is just like the acceleration tower generated by my website, except once again it's controlled directly by the firmware, increasing acceleration by 500 every 5mm. That means we start off with the lowest setting of 1500mm per second. By mid-print it's up to 3000, and by the time we reach the top we're all the way up at 7000mm per second. And here are my base results. Looking from the front, even at 7000 acceleration, this printer produces very little ringing, testament to its quality. Looking from the side of the test print, the ringing is more pronounced. And as we might expect, it gradually increases in amplitude the higher the acceleration value. Normally at this point, we would put markings on the test print, measure the distance between them, count how many oscillations are in between, and use the formula on the page to work out the resonant frequency for the X and Y axes. We can then come back to our configuration file, enter this in, as well as selecting an input shaping algorithm, of which there are currently 6. Save all of the settings and reprint the test. But I didn't do any of that, because this machine is fitted with an accelerometer, and using that we can automate the whole process. Firstly, an accelerometer is an electronic device to measure acceleration, and you've probably got one in your phone to know when the screen has been flipped and to use with other apps. The one we need for our machine is an ADXL345. It's sold by many different vendors, and the one I ordered was this one from Adafruit. There's already a shroud with mounting for this on the Ever Community Contributions page, but I had to remix it to widen the spacing to 19mm, and I also removed any covering over the center of the fan. With the accelerometer firmly mounted to the carriage, we now need to wire it back to the main board. On most 3D printers, this involves wiring it into the input-output pins of the Raspberry Pi. And with that, we need to install extra packages on the Pi to get everything working. But for the rat rig, everything's been set up to wire it directly into the main board, and this simplifies things greatly. Thanks to the pre-made RatRig vCore OS package, there's already a configuration file set up for the accelerometer. In our printer configuration file, there's already a link to this, so all we need to do is to delete the hash at the front to uncomment it and make it active. We also need to copy and paste the second half of the lines back to our main configuration file and update the probe points to be the center of our bed. Following this, we save and restart the firmware, and that's all of our software changes made. As for the actual wiring, I originally made up my loom from this thin gauge ribbon cable, but I found that it was unreliable, I assumed from voltage drop. Therefore I needed to make a whole new loom from thicker gauge wire. That wasn't too hard. Probably the worst part of this job was having to rewrap all of my print carriage cabling. With all of this in place, we get to the easy bit, the automatic calibration. We start by sending the command accelerometer query, and this error is what made me realize that my wiring wasn't up to scratch. So with the wiring fixed, this is what we should get instead, a readout from the accelerometer. Another test command we can do is measure axis noise, and that should again return some data to tell us that the accelerometer is talking to the firmware. The Klipper instructions then suggest that we test the x-axis followed by the y-axis, run some scripts on the Pi to generate a graph that we can manually interpret. But the process can be simpler than that. First of all, we start by homing the printer. That will move the carriage into the position we specified in the configuration file. We can now paste in the same command we did from the tuning tower to set our shaper frequency to 0, followed by the simple command shaper calibrate. What happens now is really interesting. The printer, for each axis one at a time, will shake the carriage back and forth at different frequencies, which constantly increase. At the low frequencies we start with, this is actually quite an obvious movement. What the firmware is doing is shaking the carriage and getting feedback from the accelerometer to find out which frequencies resonate more than others, and that's where we're likely to find our ringing. The frequency will gradually increase to the point where we can't see it, but now we can hear it. When the x-axis is done, this same test will be repeated for the y-axis. When the testing is done, we have all of the output results, and it's going through different combinations to find what it thinks is best for our machine. You can pretty much ignore all of that, click on Save Config, send this, and that will restart the firmware with the changes in place. And if we scroll to the bottom of our printer configuration file, we can see that all of the input shaping settings have been automatically placed for us. To test the results, I printed the tower once again, as before, disabling pressure advance, but this time adopting the new input shaping settings. And here are the results, and I hope you agree they're quite impressive. Our original print up the top had some fairly significant ringing, but down the bottom we can see this is greatly reduced. Remember, this is all automatic, with no thinking involved at all. If you recall, there's different types of input shapers, and it seems to me like they increase in strength as we go down the list. I experimented by changing the shaper to the most aggressive one for X and Y. And here are the results. When we look at the front surface, we started with some obvious ringing, and now it's reduced to practically nothing, particularly on the right hand side. On the side of the print, the ghosting we had is completely gone. When we flip it around to the back showing the X, we can see up the top we had quite a lot, and now down the bottom it's practically gone. And as for the final side, it's hard to film, but the result down the bottom is nearly flawless. There are some considerations to keep in mind. For instance, this gap is meant to be 0.1mm, but it opens up as the acceleration increases. You can also see that the two upper bands still have a little bit of visible ringing. So with both of these in mind, you can come back to the lines we set up earlier in our main configuration file and lower the max acceleration from 7,000 to a value that you think works better. To me, this really is like magic. And it's worth noting that if something changes like the belt tension, you do need to rerun the calibration, so I'm going to leave my accelerometer in place for convenience in future. With everything set up, let's do some fast test prints. First up, a benchy, retaining the settings from the tuning tower. That means a true 100mm per second for all external surfaces. Here are two benchies, the one on the left with the fancy stuff turned off, and the one on the right with everything turned on. What surprised me here was how much pressure advance seemed to reduce the zits on the layer changes. Although you can see on the chimney that's still pretty bulbous, and I've got some work to do in tuning. Apart from that, this benchy was a tad over half an hour and looks remarkable considering the little tuning that I've done. Next up, something to test accuracy, and do yourself a favour now and go spend $4.50 on this foldable Willys Jeep from Goo Design on Fab365. For this one, I upped the base speed to 140mm per second, but reduced the solid infill to around 100 and the external perimeters to only 90. This would be a great test if the input smoothing would lower the accuracy of the printed parts. But in fact, there was zero problems. Everything was free and loose as it came off the print bed, and now comes the fun part, rotating and positioning the parts to assemble the model. Everything is print in place without support material and simply snaps together to make the final object. There's some clever touches like using a piece of spare filament to make the steering column, and the final result is just so cool, with this removable jerry can and a number of the components being articulated, such as all 5 wheels, the front windshield, as well as the bonnet opening to reveal an engine inside. As far as designing for 3D printing goes, this is as good as it gets, and I'm really happy with how it turned out on the rat rig. One more, this time something more decorative with this Blink Fox. I retained the same settings as before with 90mm per second exterior perimeter speed, but I lowered the layer height to 1.5mm. This one was run overnight with the camera finally configured to be 1080p, and because the bed moves down, we get an octolapse type effect. And what can I say, this is one of the prettiest 3D prints that I've ever done, and when you consider the higher than average feed rate it was printed with, it makes it even more impressive. Not only surface quality, but things like part cooling too. If you're wondering, the filament is X3D Pro Diamond Series, linked in the description. Honestly, I think so far I've probably done the minimum to set this machine up, but it's already printing so well. So that brings me to a frequent question, am I happy with the machine so far? Trust me, the answer is a resounding yes. Another question I had was in terms of comparing the printer to other cheaper well-known 3D printers. As you can see, the quality is already outstanding, but what impresses me the most is the speed. If we look at our Jeep, that had a predicted print time of just over 3 hours. And if we compare that to a more traditional slicing profile with a base speed of 60mm per second and a perimeter speed of roughly half that, we can see that the predicted time is almost 2 hours longer. But in reality, it will be even slower than that, because I'm running acceleration of 6000mm per second, whereas an Ender 3 comes from factory with a value of only 500. So high speed with no compromise in quality. But I still think I can push the speed a lot more, and I intend to do so taking on the Speedboat Race Challenge from Slice Engineering. I'm really excited about some of the things in this video, so please head to the comment section and let me know if you feel the same way. Thank you so much for watching, and until next time, happy high speed and high quality 3D printing. G'day, it's Michael again. If you liked the video, then please click like. If you want to see more content like this in future, click subscribe and make sure you click on the bell to receive every notification. If you really want to support the channel and see exclusive content, become a patron. Visit my Patreon page. See you next time.